Welcome to our new unit on wave properties. Today we have two primary learning targets to guide our study of light. First, you will learn to use the wave equation to solve problems involving wavelength, frequency, and speed. Second, you will explain how reflection and refraction happen using both wave and particle models. Here is the essential question. Why is it important to use both mathematical formulas and conceptual models to describe the behavior of light? Let us begin our wave review by looking at longitudinal waves. A longitudinal wave is one in which the particles of the medium vibrate parallel to the direction of wave propagation. Common examples include sound waves and ultrasound waves traveling through air or water. Imagine pushing and pulling a stretched spring back and forth to create compressed regions. The key point here is that the vibration occurs along the same line as the wave motion. The second type of wave we must review is the transverse wave. A transverse wave is one in which the particles of the medium vibrate perpendicularly to the direction of wave propagation. All electromagnetic waves, including visible light, are transverse waves. Imagine shaking a rope up and down, creating crests and troughs that move horizontally away from your hand. The key point is that the vibration is perpendicular to the direction of travel. To build our mathematical model of waves, we must understand frequency and period. The frequency of a wave is the number of complete cycles a wave source produces per second. The standard unit for frequency is the hertz, which is defined as 1 cycle per second. The reciprocal of frequency is the period, which measures the time it takes to produce one complete wave cycle. These concepts were demonstrated by German physicist Heinrich Hertz, who first proved the existence of electromagnetic waves. Along with frequency, we also need to measure the physical size and speed of a wave. We complete our basic wave terminology by defining wavelength and wave speed. Wavelength, symbolized by the Greek letter lambda, is the distance between any two successive points in a wave that are in phase, such as crest to crest. The speed of a wave is the distance the wave travels per unit of time. These quantities are connected by the basic wave equation, which states that speed equals frequency multiplied by wavelength, or V equals F lambda. Imagine ocean waves rolling onto a sandy beach, where you can measure both their physical spacing and their travel speed. This simple equation allows us to predict wave behaviors in any material. This figure helps us visualize the relationship between frequency, period, and wavelength. Both waves are shown over exactly 1 second. The top wave has a frequency of 4 Hz, which means 4 wavelengths pass a point in 1 second. The bottom wave has a frequency of 8 Hz, so 8 wavelengths pass in that same time. Since both waves travel through the same medium, their speeds are the same. As a result, the wave with the higher frequency must have a shorter wavelength. Now let us apply our mathematical wave equation to some practice problems. In our first problem, we are given the speed of light in a material as 1.5 times 10 to the 8th meters per second, and a frequency of 7.5 times 10 to the 14th Hertz. By dividing speed by frequency, we find the wavelength is 2.0 times 10 to the negative 7th meters. In our second problem, we must find the speed of a wave with a frequency of 500 Hertz and a wavelength of 0.6 meters. Multiplying these values yields a speed of 300 meters per second. These examples show how easily we can manipulate the wave equation to find any missing property. Let us summarize our learning by reviewing how the photon theory successfully bridges the wave and particle models of light. Each photon carries a packet of energy that is directly proportional to its wave frequency, as shown in the equation E equals hf. Because of this relationship, high-frequency light like ultraviolet carries far more energetic photons than low-frequency light like infrared. Furthermore, these massless, chargeless particles travel at the constant speed of light in a vacuum, symbolized by the letter C, which in Latin means celeritas, or speed. Imagine light as a stream of energetic messengers, whose physical strength is determined by how fast they vibrate. This elegant synthesis forms the bedrock of modern quantum mechanics. The electromagnetic spectrum organizes all electromagnetic waves according to frequency and wavelength. On the left side are radio waves, which have very low frequencies and long wavelengths. As we move across the spectrum, frequency increases and wavelength decreases, passing through infrared, visible light, and ultraviolet. On the far right are X-rays and gamma rays, which have extremely high frequencies and very short wavelengths. An important point is that all electromagnetic waves travel at the same speed in a vacuum, known as the speed of light. What makes them different is how frequently the wave oscillates and how much energy each photon carries. Visible light is only a small window within this much larger spectrum. This slide summarizes the main types of electromagnetic radiation and their common uses. Radio waves are used for communication, such as radio and television. Microwaves are used for cooking and data transmission. Infrared radiation is associated with heat. Visible light allows us to see, Ultraviolet radiation affects the skin. X-rays are used for medical imaging, and gamma rays are used in medicine to treat cancer. As frequency increases, the radiation becomes more energetic. Let us put Planck's quantum theory into practice by calculating the energy of two different types of light. The equation E equals hf shows that photon energy is directly proportional to wave frequency. For green light with a frequency of 5.80 times 10 to the 14th Hz, we find an energy of 3.84 times 10 to the negative 19th joules. In the second problem, the same equation is used, but the frequency is much higher. Again, we apply E equals hf and substitute the given values. When we multiply Planck's constant by the X-ray frequency, the result is 1.99 times 10 to the negative 16th joules. This value is hundreds of times larger than the energy of a visible light photon. The large energy explains why X-rays can pass through soft tissue and affect atoms more strongly. Now that we can calculate wave properties, let us explore the historical attempts to measure the speed of light.
Galileo is the first one known to try to measure the speed of light. So at night, he put somebody on a mountaintop with a lantern and a little shutter. He was on another mountaintop with a lantern and a shutter. And they said, when you see one, give me the signal back with the shutter. And he concluded, light, if it's not infinitely fast, it's faster than we can measure. Now, a guy named Ole Romer, at the time he did this, we knew that the Newtonian gravity not only described the moon around Earth, Earth around the sun, it described Jupiter's moons around Jupiter. You calculate when the moons pass in front of and behind Jupiter. What he found was that when Earth was closest to Jupiter, the eclipses occurred 1,000 seconds sooner than when Earth was on the opposite side of the sun from Jupiter. He said either Newton's laws are wrong, or we had to wait for the light to cross the entire orbit of the Earth to get to you. What's the formula for speed? Distance divided by time.
Neil deGrasse Tyson is an astrophysicist, which means a scientist who studies objects and events in space, such as stars, galaxies, and the universe itself. Beyond research, Neil deGrasse Tyson is widely known for explaining science to the public in clear and engaging ways. He uses everyday language to describe topics like light, energy, and the cosmos.
Every time we've ever measured the speed of light, we get exactly the same number. At all times.
At all times.
Correct. And we look at other parts of the universe where we see phenomenon happening. Speed of light's the same, right on up to the edge of the universe.
Cool.
So our evidence, and since as you look out in the universe, you look back in time, we can say with confidence that the speed of light is the same and unchanging across space and through the depths of time. It is the most fundamental constant of nature we know.
Yes. Yeah.
It is so fundamental that we define the length of the meter in terms of the speed of light.
Wow. Okay.
So if we make an extra measurement of a decimal place in the speed of light, that affects the length of the meter. That's how badass the speed of light is.
Right.
The photon has another view of the world. Remember Einstein, the faster you go, slower time ticks for you?
Correct.
At the speed of light, time stops.
Are you saying photons don't experience time at all? Holy crap.
So the instant the photon was created in what we call the photosphere of the sun, the outer surface.
Okay.
And then it went on its 8-minute and 20-second journey to Earth. If you're the photon, you are born and you land on someone's buttocks in the same moment. In the same moment.
Oh, snap.
Yes.
Oh, that's amazing.
You have no
concept of time at all.
Of that time passing.
Look at that.
You were born and absorbed in the same instant.
That's really cool.
Now that we know how fast light travels, let us look at how it interacts with surfaces when it strikes them. Light normally travels in straight lines until something causes it to change direction. Reflection happens when light strikes a surface and bounces back. To simplify this behavior, we use light rays, which show the direction light travels. The law of reflection states that the angle of reflection is equal to the angle of incidence. These angles are measured from a line called the normal, which is perpendicular to the surface. This rule explains how mirrors form images and control where light goes. Smooth surfaces, like mirrors, produce specular reflection. In this type of reflection, parallel incoming rays remain parallel after reflecting. This allows clear images to form. Rough surfaces cause diffuse reflection. Here, incoming light rays reflect in many different directions because the surface is uneven. Even though the directions differ, the law of reflection still applies at each tiny point. Diffuse reflection is why we can see most objects, even though they are not mirrors. This pop quiz uses a real-life situation to explain reflection. Some tractor trailers have a sign on the back. If you can't see my mirror, I can't see you. What does this mean? The sign on the back of the truck means that light must travel from you to the truck's mirror and then back to the driver's eyes. If you cannot see the mirror, then light from your position cannot reflect into the driver's eyes. Reflection is reversible, meaning light follows the same path in opposite directions. So visibility depends on geometry, not attention. The key idea is that seeing requires light to reflect both ways. This slide shows a familiar example of refraction using a pencil in a glass of water. When light from the pencil travels from water into air, it changes speed and bends. Your eyes trace the bent light rays backward in straight lines, so the pencil appears to be in a different position. This is why the pencil looks bent or broken at the water surface. The important idea is that the pencil itself has not changed shape. Only the path of light has changed. Now that we understand reflection, let us explore what happens when light passes through a surface and bends. Let us look at Pierre de Fermat and his principle of least time. According to this principle, light always chooses the path that takes the least amount of time when traveling between 2 points. When light moves from air into water, it slows down in water. By bending at the boundary, light reduces the time spent in the slower medium. Although the path looks longer, the total travel time is minimized. This idea explains why refraction happens in a predictable way and forms the foundation for equations that describe bending angles. Fermat's principle connects refraction to a deeper idea in physics. Nature follows the most efficient path. When light travels through air and enters a transparent material like glass at an angle, its direction changes. This bending is known as refraction. The reason refraction happens is that light changes speed when it moves from one medium to another. In this case, light slows down as it enters the denser material. Because different parts of the wave change speed at slightly different times, the ray bends toward the normal. At the same time, some of the light reflects off the surface, following the law of reflection. The diagram shows the incident ray, the reflected ray, and the refracted ray, along with the angles measured from the normal. The key point is that refraction is caused by a change in speed, not a change in direction alone. This is a beautiful mathematical principle that explains why light must bend to take the fastest path. This pop quiz asks how people with astigmatism see lights. Astigmatism happens when the cornea, or lens of the eye, is not evenly curved. Because of this, light entering the eye is refracted by different amounts in different directions. Instead of focusing to a single point, the light spreads out. This causes lights to appear blurred, stretched, or scattered, especially at night, like car headlights or streetlights. Here is another pop quiz. Why do stars twinkle on a clear night? Stars appear to twinkle because their light passes through Earth's atmosphere before reaching our eyes. The air is not uniform. It changes in temperature and density, especially at night. As starlight travels through these moving layers of air, it is refracted in slightly different directions. This makes the star's position and brightness appear to change rapidly. The star itself is not changing. Only the path of the light is. To calculate exactly how much light bends in these different materials, we need to introduce a quantitative scale. To calculate exactly how much light will bend when entering a transparent medium, physicists use a constant called the index of refraction. The index of refraction is the ratio describing how much light slows in a medium. It is represented by the letter n and is calculated using the formula n equals c divided by v. Here, c represents the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. The variable v represents the speed of light inside the material. Let us put this formula to work by solving a few practice problems for common substances. Let us put our formula into practice by calculating how fast light travels through water and glass. By rearranging our equation to velocity equals speed in a vacuum divided by the index, we can find the speed in any medium. We compare this to a vacuum, which is a space entirely empty of matter. For water, with an index of 1.33, the speed is 2.26 times 10 to the 8th meters per second. For glass, with an index of 1.50, light slows to 2.00 times 10 to the 8th meters per second. To answer the essential question, using both mathematical formulas and conceptual models to describe the behavior of light allows for a deeper understanding of its properties and interactions. Formulas provide precise, quantitative predictions, while models help visualize and explain phenomena like reflection and refraction in more intuitive ways. It is time for your exit ticket to show what you have learned about wave properties. First, what is the difference between mechanical and electromagnetic waves? Mechanical waves need a physical medium to propagate, while electromagnetic waves do not. Second, how do you calculate the energy of a photon? You use the formula E equals hf. Finally, why does light bend when entering a new medium? It bends because its speed changes. Make sure you complete your answers before leaving.